All right, so we're going to talk about this second part of 15.4. All right, so just a reminder of what Green's theorem tells us. Green's theorem says, now a couple of important things that I'm not writing down. In the plane, Green's theorem applies only in the plane and only for a closed path. So the line integral around a closed path of m dx plus n dy equals the double integral over the region enclosed by that closed path of the partial of n with respect to x minus the partial of m with respect to y times dA. And we applied Green's theorem in several different ways on Friday. Often that double integral is easier to evaluate than the line integral, especially if you're talking about a piecewise smooth closed curve. And we saw in one of our examples, if this quantity dn dx minus dm dy equals 1, the line integral becomes the double integral over our region of just dA. This quantity evaluates to 1. And this is the area of our region. So what we want to do now is arrange, if we're interested in finding an area, we're going to arrange it so this is the case. So, for example, we have a difficult region that we want to find the area of. Well, we're going to invent a field over that region such that dn dx minus dm dy equals 1. And then we can find the area of the region by evaluating this line integral. All right, so that's what we're going to do here. We're interested in area. Well, we're going to invent a field so that this evaluates to 1. So we can find the area using a line integral. So our theorem. And we have 3 choices. The area of a region R bounded by a piecewise smooth simple closed curve C is given by, I'm going to write three integrals here. Our area is going to be 1/2 the line integral around our curve of minus y dx plus x dy. This is the only way that our book lists this, and it kind of doesn't make sense to me because it's usually easier to say this area is equal to the integral around our curve of minus y dx, and that equals the integral around our curve of x dy. And I'm just going to write down 1, 2, and 3. No. So see this is 2 different pieces. So if you add those 2 together, you get twice the area, so you have to divide it by 2. I don't know why our book only gives this one. These two are usually easier. For number 1, we're saying that m equals minus y over 2, and n equals x over 2. And when we take our partial derivatives, dn dx minus dm dy, we get 1. For 2, what we're saying is that m equals negative y, and n is, the 3 equals signs means identically 0. It's 0 everywhere. Not that it evaluates to 0, that it's identically 0. And then when we take our dn dx minus dm dy, we get 1. And for 3, the field that we're inventing, we're saying let m be identically 0 and n equal x. And then when we do dm dx minus dm dy, we get 1. One of these two is usually easier to work with. So we can find the area of a region by doing a line integral around the boundary. And like I mentioned on Friday, you can use this idea to come up with a formula. There's a problem in the book. I don't assign it, but I was assigned to do the proof in one of my classes. You can use Green's theorem to find a formula for the area of a polygon given only the coordinates of its vertices. And you just apply this repeatedly between each vertex, and you come up with a formula for the area of a polygon by just plugging in its vertices. It's kind of interesting. All right, why would we want to find the area by using a line integral? Let's take a look at an example. Let's say we want to find the area bounded by r of t is t squared I hat plus t cubed over 3 minus t j hat. And let me sketch a graph here. See if I can do a decent job of sketching it. This graph looks like this. Well, that's actually a pretty good graph. And this point here is x equals square root of 3. So to find the area enclosed by that thing would be relatively difficult because we'd have to set up our vertical rectangles through our double integral. We'd have to have an equation, y equals something in terms of x here, an equation y equals something in terms of x there. This, to get y in terms of x, you can see is going to be pretty not particularly nice. So what we want is the double integral over a region of dA. That could be difficult using the tools, just using a double integral. Well, let's use Green's theorem. We know that our area equals the integral around our closed curve. Probably the easiest to use is x dy by Green's. Well, x is t squared dy. Take the derivative of this. dy is t squared minus 1 dt. And when x equals square root of 3, we can get t equals plus or minus square root of 3. So our integral becomes the integral from minus square root of 3 to square root of 3 of t squared times t squared minus 1 dt. Easy integral to evaluate. And we plug that in our calculator, we can get approximately 2.77. And we would get the same value if we evaluated minus y dx, or 1/2 minus y dx plus x dy. Difficult double integral turns into an easy line integral. Yeah.
But why would you ever want to use the 1/2 y dx?
I don't know.
X dy one?
I don't know.
You just wouldn't call that one?
I don't know why that's the only one our book shows.
But is there any case where that would be?
I can't think of one where it would be easier, because you have to do this part anyway.
No matter what.
Right, you have to do that part anyway.
Why not just do this?
I don't know. I just included it because that's the only way that our book shows to do it. Just so you will have seen it. So if you see it in there, you say you know what they're talking about. All right. Questions? This application of Green's theorem doesn't show up extremely often, but when it does, it's extremely useful. All right. So what I want to do next, we're going to leave Green's theorem and area behind for now. That's really all there is to Green's theorem and area. What I want to do is come up with some alternative forms of Green's theorem that kind of preview where we're going when we start talking about these ideas in 3 dimensions. Yeah, there's not too much to this. Once we know Green's theorem, then this kind of drops out pretty quickly. All right, alternate forms of Green's theorem. So for this first one, we're going to let our field f be m I hat plus n j hat plus 0 k hat. So we're thinking of this as a 3-dimensional field, but it's in the plane. So we can apply Green's theorem. And the reason I want this to be a 3-dimensional field is we want to find the curl. Del cross f. So del cross f, just a reminder, I hat, j hat, k hat, this determinant form. And we have m, n, and 0. So when I take the curl, I get minus the partial of n with respect to z I hat plus the partial of m with respect to z j hat plus dn dx minus dm dy k hat. That look familiar? That's the quantity that's in Green's theorem. Now we're going to look at del cross f dot k. This is just going to give us this quantity. And what this represents is the vertical component of the curl. So if we take the curl of this field in the plane, the vertical component is this quantity, dm dx minus dm dy. And we can write by Green's theorem the line integral of m dx plus n dy, and again, that's a reminder, that's the same as f dot dr. This is a vector line integral, equals the double integral over our region of dn dx minus dm dy. So we're kind of using Green's theorem in reverse. We do the double integral over our region of that quantity, we get the line integral around our boundary. So what this tells us, that the line integral of the tangential component, f dot dr, remember when we came up with our vector line integral, we were finding the tangential component of our field. We did f dot t, unit tangent vector. So we're summing the tangential component. That's this part. So the line integral of the tangential component of f around C equals the double integral, the sum of the vertical component of the curl of f over R. So this when we talk about this in 3 dimensions, we're going to relate the line integral around a boundary to the sum of the vertical component of the curl over a surface. So the vertical component of the curl tells us something about our field circulating around the boundary. The tangential component tells us the tangential component around the boundary tells us the tendency of the field to cause a rotation. So the vertical component of the curl is related to something that has to do with the rotation, the tendency of the field to cause a rotation. And we're going to extend this into 3 dimensions. The last theorem that we'll talk about in the chapter is Stokes' theorem. So there's a relationship between the vertical component of the curl of a field and the tangential component of the field around a boundary. All right, that's kind of a big deal. And this is also a generalization of the fundamental theorem of calculus. We've talked about that. Green's theorem is, and this is, we're taking the integral of some quantity on the boundary of a region that's related to some other quantity on the interior of the region. So the integral over an interval in Calc 1 is related to some other function that's related to our original function at the boundaries. The integral of some quantity on the interior of a region is related to some other quantity on the boundary of the region. That's really what this, in big picture, what this is telling us. All right, questions? All right, we're going to come up with a similar expression for the outward component of f over the region, or the normal component of f. So I'm going to say now, look at the normal component of f. And I'm going to say in the plane. And by normal, I mean outward, normal to the curve that bounds our region. All right, so we're going to let our curve be given by r equals x of t I hat plus y of t j hat for a less than or equal to t less than or equal to b. And this is going to be a simple closed curve in the plane. And we know that our unit tangent vector from what we did in chapter 12, t is r prime over the magnitude of r prime. And in this case, that's x prime over the magnitude of r prime. I'm just writing this in component form. I hat plus y prime over the magnitude of r prime j hat. Thank you.
Sure.
And we know that our unit normal vector, so our unit tangent vector is tangent to the curve. The unit normal vector is going to point orthogonal to the unit tangent vector. So we can switch these two and change the sign on one. But we want the outward unit normal vector. I'm going to say n, I'll use a small n. And that's going to be, the way I'm going to rearrange this is y prime over the magnitude of r prime minus x prime over the, not r double prime, r prime, I was getting excited, r prime j hat. And the reason I picked that is if we're in the plane here, this is an I hat. If we're in the plane, and this is some curve, and my unit tangent vector is here, we see that we need the y component to stay positive, but the x component, or we need the x component to be positive and the y component to change directions. So this would be n. And these are orthogonal. So that's my outward unit normal vector. And we're going to let f be m I hat plus n j hat. And we're going to sum the normal component of f around the curve. So we're going to find the line integral around our curve of f dot n ds. So we're summing the normal component, just adding up all of those normal components at each point around the curve. Well, that's going to be the integral from a to b of m I hat plus n j hat dot this unit normal vector dot y prime over the magnitude of r prime I hat minus x prime over the magnitude of r prime j hat. ds. Make sure my prime is showing up there. There we go. So I do my dot product, and this is going to equal the integral from a to b of m y prime over the magnitude of r prime minus n x prime over the magnitude of r prime. And some of us might be able to see where we're going here. ds. What's another expression that I can write for ds? ds equals magnitude of r prime dt. Those r primes in the denominator are going to cancel out with that r prime in ds, and I get the line integral around our curve. We're summing the outward component of f ds equals the integral from a to b of m, well, y prime is dy dt, minus n x prime is dx dt, dt. Well, now the dt's go away. So this equals the line integral around our curve of minus n dx plus m dy. Well, now we have a line integral around a closed, simple closed curve, piecewise smooth, simple closed curve over a region. We can apply Green's theorem. Now notice these are in the opposite order that they usually are. Usually we have the m with the dx and the n with the dy, and both are positive. So we're going to apply Green's theorem. The line integral of the outward component of f around our boundary equals the double integral over a region of dm dx minus negative, so plus dn dy dA. All right, well, hold on a second. What is this quantity dm dx plus dn dy for our field m I hat plus n j hat? Partial derivative of the first component with respect to x plus the partial derivative of the n with respect to y. Not the gradient, but the divergence. That's the divergence of f. Yeah, eventually, it's vector stuff, gradient, orthogonal, unit normal vector, unit tangent vector, curvature, acceleration. Total derivative. Differential, sorry. We're just trying to. That equals del dot f, the divergence. It's always, when you do math, and you get to a point where you can say, but, that's always a good point in your proof, your demonstration, because that means you can substitute or you get rid of. So that tells us that the line integral of the normal component of our field around this curve is the double integral over our region of the divergence of f. So we're saying in words, the line integral of the outward component of f around C is the double integral, the sum of double integral of the divergence of f over the region, over R. So what this tells us is the divergence of f is related to the idea of the field going out of our region. And when we extend this to 3 dimensions, this will be our divergence theorem. And we'll relate the divergence out of a volume. So we'll have a triple integral here. And we'll relate that to the outward normal component of our field over a surface. So the outward component of our field is related to that divergence of the field over our region. So the divergence tells us something about the field flowing outward. All right, and the main reason I wanted to do this was to set up our divergence theorem and our Stokes theorem in 3 dimensions, which are a little more difficult to prove in 3 dimensions, but not too bad in 2 dimensions.
But it's basically the same.
Basically the same idea.
Group of arguments. It's
Yes.
just a lot longer to get to this point.
Yes. All right, questions? That was a lot of math.
Yeah. Yes.
And one thing that's really nice about that we just did